Hi, welcome to this video. I've been in the software industry for over 30 years, predominantly writing code, and I come from a reasonably good mathematics background and have spent a lot of time dabbling in the worlds of artificial intelligence and machine learning and related stuff. And so I often get asked my opinion about what the potential is, the real potential is, for AI generated code to add value to a business, and possibly also what are the pitfalls, what are the shortfalls. And that is why I have put this video together. This is my attempt to try and answer those questions in a balanced way without being particularly biased in any direction. We all hear a lot of hype coming out, notably coming out of vendors and people who have very probably vested interests in their positions, telling us that the world is going to change, spinning and in the other direction, and Mars is going to turn bright green and all sorts of things because of AI code. And we do have to question a lot of what these statements have as a message underlying the words that you hear, because there are certainly a lot of vested interests, but there are also, I get the sense, of a lot of people making statements who have no idea what it actually means to write code, good code, for a living, what it means to build software, to engineer software. And that is, I think, a big difference that a lot of people need to try and understand more about. But let's start with the good news. So sure, caveat emptor, we do need to be aware of what the risks are, and I'm going to try and point out some things that you should be aware of if you are not sure how to measure the value of AI code. But there is good news. The good news is that large language models can generate code that works for some circumstances. Not for all circumstances, but certainly for some circumstances. And this is great news. And when you know what you're doing and you understand the risks, you can significantly improve your productivity as a developer or as a development team. And I certainly personally, I do this. But you do need to understand the dark side. And this is the problem. The dark side can be quite dark. Because if you have something that generates code for you, how do you know if it's good code? How do you know that it's of more value than code that a developer, an experienced software engineer, could have produced instead of an AI model? And this is a very, very deep question, and I don't want to spend too much time, but I'd like you to give some thought to some alternatives or options of how would you know that the code that is being generated, instead of being manually crafted by a software engineer, how do you know that it's worth having? Well, you could do manual testing, but this is time consuming. And obviously testers make mistakes, they overlook areas, there are scenarios that they don't test. You could have an experienced software engineer review the code. This also has oversight risks, but it's also extensively more expensive typically than manual testing, because now you need an experienced software engineer, not just a junior tester, to evaluate the code. And this is really a challenge, because notably AI generators can often generate a lot of unnecessary code. So they can produce code that works, but also includes code that is completely superfluous, is not at all related to the outcome of the code, and will just confuse the outcomes of any code review or manual examination of the code. A lot of industry pundits should be ashamed of themselves by saying, oh, I never even look at the code that is generated for me. Well, you can automate code testing, because that's what they will say. They'll say, oh, I don't need to understand the code, I'll just test it with automated testing, and then if it passes the tests, life is good. Yeah, sure, but automated testing is expensive. It means not only do you need to have the code, you need to have very often what are known as unit tests, which is more code to test your code. And you get into the situation of, well, who guards the guardians? Who is going to test the test code? This becomes an extremely expensive quagmire that a lot of software development teams get into. They love the concept of test-driven development, but it turns out to be hugely expensive, more expensive than the opposite of not having test-driven development, and also it does become very difficult to maintain. A lot of the times, another problem is people will maintain the code, the actual business code, because they're under pressure to deliver a deadline, but they won't make the related changes or the matching changes to the test code. And then as soon as you get out of sync, you may as well not have your automated tests in the first place. Very, very simple concept. There's also, in truth, some things are really very difficult to test. We're going to be playing around with a prime number filter for reasons that I'll cover later. And we'll use generated code and evaluate it. But the problem with prime number filter is that prime numbers are notoriously difficult to detect when you are working with very, very large integers. This is why we use prime numbers in cryptography. So if you are trying to automate testing for a prime number filter and you are using randomly generated large test inputs, there's no chance you're going to be able to build a test harness that will perform, that will give you quick test results, because you could be waiting an infinite amount of time to get your test results. Similarly, a pseudo-random number generator. How on earth do you automate testing? How do you know that the number that you have generated is random in a series of numbers? It doesn't help to compare with previous numbers, because it's possible that repeated outcomes could also be random. There's another thing that you need to think about here when you're considering the overall value of generated code, is that you need to consider the impact on your business or on your environment for the code, and also what the complexity is. For example, very often our software architecture, we split our code into back-end code and front-end code, the user interface code. And the back-end code is where all our business critical decisions are made and all the important calculations are done and all of the updates to databases occur, the critical code. But in the front end, we don't have any significant critical code there at all. We don't make any critical decisions. We're just trying to make screens look pretty. So I personally, for example, I never manually write UI code anymore, user interface code. I just generate it. Because if I don't like it, I can just throw it away and generate more. Whereas back-end code needs rigor, it needs robust testing, it needs to be trustworthy. And so very, very different outcomes require different approaches. Another thing you really need to understand is that whether or not your code works is not the entire picture. The fact that your code may add 1 + 1 and come out with 2 is not the full picture. Let's call it the functional requirement. The direct requirement for your code we often refer to as the functional requirement. But when we are designing and building software solutions, we have to consider non-functional requirements. And some of them are kind of obvious, things like it must perform well. So the code shouldn't be so slow that users will lose interest. And also the performance should be predictable. In other words, if you run the code twice, it should perform in reasonably the same amount of time each time, or complete within the same amount of time. So consistent performance is often an essential criterion for acceptance of software as a solution. Scalability kind of ties up with performance in a sense, in that the more users you add, the performance shouldn't deteriorate rapidly, and that's often a consideration for large scale applications with millions of web users or whatever. Security is typically a non-negotiable. Security is something that we have to consider. Often we operate in an environment where we could be subject to legal damage if we disclose customers' data or things like that. So security is an obvious one that needs to be there. Maintainability is critical. You start your software, running your software today, but if you need to change it over time and maintain it, will you be able to maintain the software? Is a critical thing. Can you afford to maintain the software? Affordability and maintainability often are two edges of the same sword, and you need to think about that, because if maintaining the software is complex, then you could need to employ more skilled software engineers for maintenance, and that will increase the cost of ownership of your software. And if your software team cannot understand the code that has been generated, then they won't be able to maintain it, and therefore the cost of ownership of that code will go up. As I said earlier in the previous slide, that some people say, well, I'm not going to maintain it. If it's generated, I'll just throw it away and regenerate. That's not always viable. Very often you have multiple systems that integrate with each other, and they are codependent on mutual testability. Another thing that people often forget is compliance. Compliance is a really tricky one when you consider AI-generated code, because security, in comparison, security is universal. We make universal assumptions about things that need to be protected in software, irrespective of where you're operating around the world. You want to protect passwords and data and all that good stuff. But compliance requirements change in regions. So it's very possible that the model you're using was trained to generate code in a region that has radically different compliance requirements from yours. And so the code that it generates is based on a model that has a different interpretation of compliance realities in your business space. We're going to, for the rest of this video, focus on the two simple ones to address in reality: our performance and maintainability. Security, and really important, obviously, and compliance, but they're really difficult to measure and would take many, many days. So we want to keep this short and sweet. So we're going to focus on performance and maintainability. Okay, so to get a better grip, better understanding of the pros and cons of AI-generated code, we're going to look at a prime number filter. We're going to look at code that we're going to ask AI to generate for us, that basically we can give it an integer number, a value, and say, is this a prime number? Yes or no. Why this requirement? Well, everybody knows pretty much what a prime number is. A prime number is any integer value above 2, and including 2, that is only divisible by 1 and itself. And when we say divisible here, we're speaking mathematically divisible. Divisibility in mathematics means without a remainder. So a prime number is a number that can only be divided by 1 and itself without a remainder in the result, and that's really important. So we know what a prime number is, and it's a well understood problem, and as a species we've been working with this problem for a long time. Eratosthenes, famously in the 4th century BC, developed what we now call the sieve of Eratosthenes to establish a set of prime numbers in a range of values. But the point for us is that we know how prime numbers are determined, so it's kind of easy for us to verify outputs. The only problem is, for automated testing, we need to consider that very large numeric values require extremely long periods to assess primality for. So that's a caveat, but let's ignore that for the moment. But it's also interesting that because of the opportunities that exist for optimizing a prime number filter, which we'll discuss shortly, it's possible that any AI could naively generate code that is very suboptimal. There's a wide range of performance optimizations for prime number filters that we'll discuss that maybe an AI code generator could overlook, maybe because the sample code upon which it was trained did not include those optimizations or didn't cater for those optimizations. The challenge is that something like a prime number filter could, because it's so well known, AI models could establish it well and have seen lots and lots of samples. So the problem with our example here is we're not really expecting the AI model to reason, because it could just spew out solutions it's seen before. So what we're going to do is we're going to make its life a little bit more complicated. We're going to intentionally frustrate the requirement a little bit to see if the AI model is capable of reasoning about specific aspects of the requirement that are not normally associated with a prime number filter. And we're doing this intentionally. And there's also a risk that the LLM models could just be doing a simple copy and paste, an educated copy and paste, if you will. And we want to be aware of that, because that incurs risk that possibly we need to be in a position to mitigate in the future if it occurs. So we'll have a look at that. We'll have a look at how we can assess the risk of something like that happening. Okay. So what we're going to do for our first experiment is I have chosen, and I'm not going to disclose the identities, and I'm not going to show you the actual generation of the code, but I have chosen two of the world's top, most renowned AI providers who are known not only for generating code, but for other things as well, other things that the AI models can do, and they shall remain anonymous. What I'm going to show you, I'm showing you right now, is a prompt that I submitted to one of these providers. This provider has a couple of models on offer, from more expensive and ostensibly more complete to cheaper and maybe less expert. So what I'm going to do, what I did, is I took this prompt, literally that you see here on the screen in the white block, and I submitted it to one of the AI providers, and I submitted it to both its most expensive and its commodity least expensive model. Exactly the same prompt. And maybe to clarify a couple of things here, so I use the term function here, generate a static function. Technically in C#, it's a method, it's not a function. I know that. We're not here to get involved in semantics. What we want is a little chunk of code that we can provide it with an argument that says, here is a large unsigned integer. Remember that a prime number can never be negative. It's only a positive value from 2 upwards. And it could be a very big number. So an unsigned long integer means a 64-bit integer. That's what we want to give it, and we want it to say yay or nay. Is it prime, yes or no? Return a Boolean value, true or false. That's it. And so that's the requirement. The top half of the white block is the actual requirement. The bottom 3 lines are the nuisance. They are the rubbing the salt in the wound. So we are saying, if the argument has a value of 47, 49, or 42, always return false. If the argument has a value of 43, always return false. And if the argument has a value of 41, always return false. Now this is patently annoying if you can think it through, because anybody who understands prime numbers knows that there are only 3 prime numbers between the values of 41 and 49. They are 41, 43, and 47. For example, 49 is 7 times 7, and 42 is 7 times 6. So they're not prime, but 47, 43, and 41 are. So if the model was capable of rationalizing, of applying reason, it would be able to say, I can basically just say anything between 40 and 50, ignore it. If it generates lots of code to deal with these individual values as individual values rather than as a range, then that's superfluous code. That's excess code that reasoning should have eliminated. So what I'm looking for is something that can do prime number filtering correctly, but also that implements those last 3 requirements, or in fact 5 requirements stated in 3 lines, with the least possible amount of code intervention. So what we're going to do is, well, not what we're going to do. What I did was I submitted this to this provider, and I got 2 responses, one for the expensive model and one for the cheaper model. And then what I did was I put them into a test harness, which we are going to have a look at. The test harness is C#. It's an application. It's a C# console application. If you're not familiar with C# and you want to learn more, please go to patreon.com incremented, and you'll see we have a course in YouTube on learning C# that should get you there. But ideally what we're going to do is we're going to take the generated code, we're going to plug it into a test harness in C# that will allow us to assess the performance of this code, and we're going to compare it to some prime number filtering code that I have optimized manually, and we'll see what we can get as a result. Okay, so in order to assess the adequacy, the performance of this code that we are going to get back, we're going to test it by saying, well, for example, tell me how many prime numbers you can find within a range of numbers, let's say between 1 and 100, and we know that that result should be 25. However, we're going to exclude our 3 exceptions between 40 and 51, so actually we'll get 20. If our code is working, we'll get 22 rather than 25. So that's the first thing, is we want correctness from the code that is generated. But we also want to try and get optimal performance. Now there's a couple of things that we can do, and it helps to understand how a prime number filter would work in order to understand the optimizations. Let's say, for example, we were trying to find out if 6 was a prime number. What we could do is we could start at 1, but we know 1 will always be divisible, 6 will be divisible by 1. So we normally start at 2. And we'll say, is the number that I'm looking at, 2 or 3 or 4 or 5, the numbers below the number we're filtering, is it divisible by the number that we're considering? So if 6 is divisible by 2, i.e. 6 divided by 2 is something without a remainder, then it cannot be a prime number, because remember, the number can only be divisible by itself and 1. So if it's divisible by 2, then it's not a prime number. So in this case, 6 is obviously, it would fail at number 2, at 2. It would say, no, 6 is divisible by 2 in addition to being divisible by 1, so it's clearly not a prime number. Even if we had not checked 2, we would then go on and check 3, and 6 is also divisible by 3, so clearly 6 is not a prime number, and so on. But had we got to 4, it's not divisible by 4. 6 is not divisible by 4 because there's a remainder, and it's not divisible by 5, there's a remainder, and so on. So this is how it goes. So what we're showing here is, if we look at some sequences that I've got in this table, here we're checking up to 8. So we're saying, let's see what would happen if we were trying to figure out if 8 was a prime number. Well, we don't waste our time checking 1 because we know everything's divisible by 1. If we started at 2, we would immediately know, after just checking 1 number, we would know that 8 is not prime because it is divisible by 2. 2 times 4 is 8. However, if we'd started at 3, we would get a remainder. And then we go into the next one. Here's an interesting thing that you do need to be aware of, is that there's a reciprocal. So 2 times 4 is 8, but also 4 times 2 is 8. So the 2 factors of 8 balance each other out. And this is an important relationship. If you look at this, that 2 times 4 is 8, but also 4 times 2 is 8. So if 2 times 4 is 8, obviously 4 times 2 is 8 as well. You don't need to check both. But wherever you get an X, that says there's some kind of remainder, therefore go on to the next check. For 8, we would stop at 2 because we'd immediately know that 8 is divisible by 2, therefore it can't be prime. 9, well, we'll get to 2, it's not divisible. We get to 3, because 9 is a perfect square, it's 3 times 3, that's when we would say, no, it's not a prime. However, if that wasn't the case, we would carry on until we got to 9 times 1. Let's look at, but 9 we know is not prime, because 3 times 3 so 9 is divisible by 3, in addition to being divisible by 1 and itself. If we look at 11, we can say, okay, well, it's divisible by 1, it's divisible by itself, but there is nothing else between 1 and 11 that it is divisible by without a remainder. So therefore, 11 is prime. And and so on. So 16 isn't prime because we've got these pairs of factors, 8 and 2, 2 and 8, and then 4 times 4 because 16 is a perfect square. 17 is prime. And so we're going, oops, that's a typo, I should fix that slide. But here we've got 1 and 17 works, 17 and 1 works, but nothing else produces anything other than something with a remainder. Nothing else is divisible. So 17 is prime. 18 is not prime. We've got the matching factors. So we've got 2 and 9, we've got 9 and 2, we've got 3 and 6, and 6 and 3. So we know that. But what is interesting is looking at the square root of the number that we are checking. Because we quickly learn that we actually only have to check up to the floor of the square root of the number. So let's say if we went to 9, the square root of 9 is 3. Okay? It means that we would never need to go above 3 in our checks, because everything above 3, if you look here, is a reflection of what happened before the square root. In other words, if you have checked up to the square root, then anything for that number, and floor, by the way, means just take away the fraction. So if you take a square root of, let's say, for example, 16 is 4, so the square root of 13 would be 3 point something or other. There'd be a fraction. So just round it down to 3. Round it down to the lowest integer. And this is a simple performance optimization rule that works extremely well for prime number filtering, is that we only need to check up to the floor of the square root of that number. So for 18, for example, 18, the square root floor is 4. So when we get up to 4, if we haven't had a result by then, we know we can stop checking. It's the maximum check. So we wouldn't have to do 18 checks. We would only have to do 2 checks, 2 and 3, because 1 we don't need to check anyway, and 2 and 3 we can check, but there's no point going above that because that's the square root. So anything here would be reflected on the other side of the square root, and this is a fundamental important rule. So what we do when we are checking for prime filters, or implementing a prime filter, what we can do is we can say if the number is less than 2, it's not a prime, because that means it's either negative or 0 or 1, and a prime can only be 2 or greater and an integer. If it's 2, it is a prime. Don't even bother to check. Just immediately say, yep, it's prime. If the number is divisible by 2, don't waste your time, because it's a multiple of 2, therefore it's not prime, and we saw that already. This also, by the way, applies for any future prime number that we detect in the sequence, and this is how the sieve of Eratosthenes works, by the way, which is not particularly relevant to our discussion right now, but that's just geeky for your interest. So if none of those top 3 checks works, so if you get to the stage where it's not less than 2, it's not 2, and it's not divisible by 2, then what we do is we go from 3 onwards and we check up to the floor of the square root, up to and including the floor of the square root, and see if the number we're checking, if the target number is divisible by that number. If they are divisible, then the number is not prime. For example, here we find a number that is divisible, that is not prime. So then we say, no, this is not a prime number. If we get all the way through all of these checks, maybe we didn't have to do the brute force check, which would be great because it takes time. But if we got to the end and we haven't found a situation, then we say, yep, the number is prime. And this is how a prime filter typically works. It's also not obvious, and even more geeky than maybe you need to know, but the square root function is typically implemented using a mechanism called Newton's method, which is iterative. It means that it is quite costly in code to use the square root function in typical implementations. We'll come to that later. In fact, it's normally far more efficient to take the number and multiply it by itself and then see if that result is less than or equal to the number, rather than checking if the c is less than the square root itself. Please, if you don't get this right now, I'd encourage you to go to patreon.com, Incremented, and download these slides and then have a look, have a think through it yourself, and you'll see that you can also test it with some simple C# code to see in 100 million times how long it takes to calculate the square root of a number versus multiply it by itself and get the result. Okay, so now that we know a little bit more about how we're going to, or our expectations of prime number filtering and how the prime number filter could be optimized, we're going to look at the code. Okay, so here is my simple little C# console, .NET console app project. As I said, if you're not familiar with C# and .NET, please have a look at our C# Essentials course. Hopefully it would get you up to speed. But basically, so this is an example of why AI code can be a bad idea, possibly an understatement. This is our prompt. You'll be able to download this and try it yourself. If you don't believe me on any of these outcomes, please go ahead, go to patreon.com/incremented and download this experiment A sample and see for yourself. Now, there's a bunch of stuff that we don't really concern about, but this is our test harness. This bunch of code here in main is the test harness. I'll come back to it. Now, this code here is prime high, was generated by the expensive model for the provider. That's where high comes from, high cost. And is prime low is the low cost generated code. And then this one down here is a sample that I hand optimized to see if I can do any better. And we'll see what the outcome of that is. So what the harness does is it allows us at the command line to select a model, either O for the optimized or high or low, H or L, and the starting and ending range numbers. Because we want to, the way that we can assess performance of a prime number filter is to give it a range of numbers and say, okay, how long does this take you to figure out, to tell me how many prime numbers there are in this range. So I can run this code at the command line and get a result. So let's say for example I say .NET high and starting at 1 to 100. Okay. High 100. Sorry, a bit of a typo there. Okay, so what this says is that we've run the high cost model code, the code generated by the high cost model, and we've said to it, how many prime numbers do you detect between the numbers 1 and 100? And it comes back and it says 22, which is absolutely correct because we told it to ignore the 3 prime numbers between 40 and 50. So that is exactly the value that we're expecting, and we can compare it with a low cost model, for example, and we'll get an equivalent outcome. Okay, it says there's 22 primes. Significantly, however, it says it took 0 milliseconds because it's a very, very small range of numbers. Let's try it with our optimized code. And hopefully we get an exact identical result. Yeah, 0 milliseconds, 22 primes. We can try it with a bigger number, let's say 1 million. And let's just run the 3 of them. Now, obviously, when you are performance testing code, you should run your tests many times. I'm only testing them once, but I do have average values that I will show you when we get back to the slides. But these numbers are roughly representative in general of what we will get. I'll run the tests once more just so that you can see. Okay, so if we try the high, the low, I'm just going to smooch this up a little bit over here and then optimize code. Okay, so we've got 2 samples. Let's see what we've got. So typically for the high cost code, generated code, we're getting 1,000 milliseconds, let's say, whatever. But we're getting the same number of primes all the time. It's always 78495, which is encouraging because between 1 and 1 million, there are in fact 78,498 primes, but we've excluded 3 of them. So that's good. So the code is functionally correct. How do we know it's correct? Well, we know how many primes to expect. And what's interesting here is that the high cost code is the slowest code we have. The lowest cost model, ironically, is almost double the performance of the high cost code from the same provider, which is interesting. And then obviously, because I have a lot of experience with this kind of thing, I'm in a position to optimize the code slightly more than the low cost code is. So let's have a look at the code. Let's have a look at what the code did to achieve these results and maybe some commentary around this. So let's start with the high cost code. This is the first problem. There's no reasoning here. The model had no ability to look at those 5 exceptions and figure out that they are all between 40 and 50 or 41 and 49 and realize that in fact there are only 3 primes in that number range anyway, so it's pointless to check anything other than 41, 43 and 47 because all of the other numbers are not prime, so you may as well just return false. So in other words, what I'm trying to say is if this model had any reasonable common sense, it would say something like if number is greater than or equal to 41 or number is less than or equal to 49, return false. Why does this make a difference? Well, it's less code, and less code means generally more maintainable code. So what we don't want is an AI model to blindly generate superfluous code that could be more optimally implemented if it had given it a little bit more thought. Clearly, there was no reasoning here. It was just blindly implementing with brute force those rules. We know that this number, remember our rules, we said immediately eliminate anything less than 2. That's great. We know that's a fundamental principle. We then start with the number 2. And we iterate through all numbers up to the square root. So it's great it knows about the square root. Some code you will see just checks up to the number, which is obviously so 18 instead of 3, for example. But this code is clever enough to know that square root is a better choice. And it increments 1 by 1 by 1. So it increments the number. And for each number that it detects, it sees if it's divisible, if that number is, if the target number is divisible by that number, and if it is divisible, then it says this is not a prime. So, okay, that is the high cost code. Let's compare this with the low cost code, which, as we figured out, is actually, it performs better. It also, interesting, and now remember this is the same company but a different model, their cheaper model. it was clever enough to combine this, all of that code into a single condition instead of multiple lines of code. Notice that this literally took the statements. If I switch back to our prompt, if we looked at our prompt, we had three additional rules. One line said 47, 49, and 42, and then another line said 43, and another line said 41. Well, that's what it's done. So there's no sense there. But here, at least the cheaper model applied a little bit more reasoning and said, well, let's combine them all into one line because it's less code, which is a great thing, so fair enough. It wasn't clever enough to figure out it may as well just check from anything from 41 to 49, or 40 to 50 for that matter, because there's only 3 primes in there anyway, and that all of the primes that exist in that number range are listed here. They're 41, 43, and 47. So it may have well just done the range check. However, it's cleverer in that it's doing the equivalent of this, that if the number is less than 2, it's saying less than or equal to 1. That's a good check. It also knows that if the number is 2 in comparison, it's automatic. Don't even check. Don't even get into the brute force loop. However, it's significantly cleverer in that it then immediately ignores any even numbers that follow. Any number that is divisible by 2, this symbol here is modulus. It's saying if the number modulus 2, in other words, if the remainder of dividing the number by 2 is 0, it's divisible, then false. In other words, it's an even number. The only even prime number is 2. Any number divisible by 2 cannot be prime. So it's immediately eliminating half of the potential numbers that we could have to check. Because if we detect non-prime here, we don't need to go to the brute force loop. Very important. It's got, I want to copy this code here because there's a subtle difference and it's really, really important. So if none of those, so this is the high cost code up there, and this is the low cost code. This is the cheaper code. The high cost code starts at 2 and checks up to something greater than the floor of the square root. Why don't I have floor in there? Well, because it's an integer. So an integer value is immediately any fraction is removed. So it's flawed, mathematically flawed. Flawed as in the floor, not F-L-A-W. So here they're incrementing 1. I++ says add 1 to it and try next. Notice that the cheaper model is clever enough to start at 3 because it's already eliminated 2, and it's incrementing 2 at a time. It's skipping 2 at a time. It's skipping the even numbers. So it's checking 3 and then 5 and then 7 and then 9. It's not bothering to waste time with the even numbers. And that is why our performance ended up as roughly half the time. It's checking half of the numbers. So it's a no-brainer to say that the cheaper model from the same provider as the expensive model actually produced far cleverer, more performant prime filter code. And that's an important number to realize. Now, some of them would say to you, some people will say to you, oh, well, you could have submitted the prompt again and got a different result. Well, then my question is, how do you know when to stop submitting? There's nothing in the model output that says, this is my best result. No, you have to keep on checking. And obviously, it's in the provider's interests for you to resubmit and resubmit because that's how they make their money. Surely, if they were going to provide a competent outcome, they should provide it as soon as possible. It should be presented to you as soon as it is known to them, which it clearly wasn't. Let's have a look at our optimized one. It's roughly the same. Okay, so I could have actually, in fairness, this should say 41 and 49. Because expecting it to reason to 40 and 50 is maybe pushing a boat out a bit far. But 41 and 49 it could have figured out it should have figured out quite easily, because it should know that there are only 3 prime numbers in that range and they were all mentioned. This is obvious, we discussed this. Any multiple of 2 return false, and then we've got the same loop of 3, and then add 2 and try again and try again and try again. And so there is a subtlety. There is no square root. We know, we're clever enough to know, if I compare the brute force check loop here, let's have a look at this. We're not calling square root. The difference between square root and Newton's method is significant. It is far faster to just multiply the number by itself and check that it's small or equal to the limit than to call the square root function because of the overhead of Newton's method. And I know this is a deep technicality, but it's a real technicality, and we can see it in our results. So we get to the stage where 506 and 390 doesn't seem to make a difference, but let's take our low model and add another 0 to it. And you start to see that these kinds of optimizations actually become quite significant. In that, so the better of the AI generated models for 10 million numbers, consecutive numbers, completes in 13 seconds, so 13 and a half seconds. Oops, sorry. But if we call our optimized model, you start to see the significance of why performance optimization of code becomes so critical, is that if you want scalability, we've basically just reduced this time taken by roughly 30%. And the difference is not calling square root, but multiplying the number by itself instead. Anyway, so that is it. We've got some clearly naive code, suspiciously looks like copy and paste, with some arbitrary implementation of rules at the top, this stuff over here. And a very naive brute force implementation because they didn't even start at 3 and skip 2. There was no check for even numbers. The cheaper model at least knew about even numbers and to skip them, which saved half the time. And then our optimization sure was a little bit better, but we're humans, so we're allowed to do that. So what does this review teach us? Well, a couple of things. First of all, it's quite clear that both the high cost and the lower cost models from the same provider and our own hand optimized code produce a correct result. So everybody's happy if all we are looking for is correctness. However, performance is radically different between the higher cost model output and the lower cost model output. We also learned that the higher cost model, in this case, produced a lot more superfluous code to implement our extra 5 rules than the lower cost model did. Now, it's quite possible that the provider of the model or one of their ardent fans would say, oh, but if you resubmitted the same prompt again, you'd get a better result for the higher cost model. How would we know? When do we stop? Do we get a refund for the first submission? These are things that we need to consider, because at the end of the day, it requires human effort to assess the outcome and decide whether or not the first output, the first result we receive from the model, is appropriate to task. Although I couldn't show all of the actual interactions with the AI providers in this video so far, or in the future, I became quite suspicious about this seeming copy and paste tendency that the models have. It became more and more clear to me that we're not looking at reasoning here. We're looking at something that has been trained on a raft of existing code and takes a best guess of what the most suitable code is in the response and provides that as the output. This is very different from a scenario in which the AI model somehow understands the requirement from the prompt in a deep, say, internalized manner, and once it obtains that rational understanding, is then capable of producing the output you asked for in any programming language that you require. And I wanted to test that. So what I did was I decided that I would simplify the prompt, get rid of the annoying and ignore between 40 and 50 requirement, and just focus on the core requirement. Go to a single provider. I chose one of the other top 3 providers for this, not the first provider. And I asked that provider to generate code for me in C# and in Go, because I absolutely love Go. Some folk would refer to it as Golang, but it's called Go. For me as a C programmer, Go is like coming home. And I thought I'd see what happens. So give me it in C#, give it to me in Go, and let's compare what it is. Because if the model is internalizing the requirement, then the algorithmic outcome should be the same. It's just the syntactical interpretation that should vary. Let's see what happened. So I had a conundrum because the code that was generated for Go by the second provider using the same model, the same cost model as the C# code, would obviously be attributed to or attributable to that provider, and I didn't want to show you that Go code. What I did was, because I work frequently with both Go and C#, is I took the liberty of translating manually the Go code into C# code so that we had an equivalent to compare with the C# that came from the provider, if that makes sense. So what we have here is another test harness, similar test harness where we have a CS and a Go function that we can call, CS obviously being the C# and Go being the C# code derived from the Go code by me manually, albeit arguably by me. The C# code is extremely similar to the lower cost code generated by the first provider. No surprises. The only difference is, instead of putting the square root here in the for loop, they calculate the square root first, the floor of the square root first, and then substitute it. That's fine. The C# compiler and the optimizer will figure out most of that anyway. We don't really care. And it turns out that the performance characteristics of the second provider's low-cost model for C# are roughly equivalent to what we saw for the first provider's low-cost model for C#. Let's have a look. We can do a .NET run, and we can do the C code, and we'll start from 1 and go to 10 million. And sure, the averages work out, but it turns out that we get pretty much the same performance characteristics from the second provider's code in C# that we do for the first provider. So roughly 10 seconds, it's for 10 million checks. That looks good. What's interesting here is if we go for the Go code equivalent, you will see that there's a shocking, significant difference. It takes roughly half the time. Now, please be clear, the isPrime Go is also in C#. Remember, I manually translated this, but the algorithm is substantially different. It's significantly different in two ways. First of all, if you compare with the C# algorithm that was the code that was generated for C#, the C# code is only checking for even numbers, stuff divisible by 2. But the Go code, derived code, is also clever enough to also check for anything divisible by 3, because 3 is also a prime number. So anything multiplied by a prime number cannot be a prime number. That's the fundamental theory of arithmetic. So here we go. So there's a radical difference. Instead of eliminating half of the potential numbers to check, we're not only eliminating half, but then all of the ones that are divisible by 3 as well. This is a radical difference. It's a huge, it's almost as if we are starting to think about the sieve of Eratosthenes here. It's basically how the sieve of Eratosthenes works, is you essentially take every prime number you discover and multiply it out and eliminate anything that can be derived from a prime number. So all that this algorithm is doing is going in that direction. And it's only doing it for the first two prime numbers, but it's radically significant, as we saw from the performance. The second thing that you'll see is if we compare the brute force loops here, let's put them next to each other. Because we are eliminating both even numbers, something divisible by 2 and something divisible by 3, the loop starts at 5, not 3, and it can skip every 6 numbers, not every 2 numbers. It can skip every 6 numbers, and it's clever enough to know that whenever it gets to a number that it should check, it not only should check that number, but should also check the odd number after it, hence the +2. And this, as you can see from the performance results, makes a huge difference, a dramatic difference. What is clear here is that this is not the same algorithm. The AI model for this provider did not internalize the requirement and comprehend it and then generate the same equivalent code in different languages for the same requirement. It copy and pasted different implementations of an algorithm that it had been trained on, that roughly matched this requirement. Well, what did we learn from that? So it's quite clear, or reasonably clear, that the second company, the second provider's commodity low-cost model produced roughly the same output as the first provider. And that's great. So you can take a prompt that describes the requirement and you're going to get a reasonably predictable output for C# from either provider, and that's wonderful. There's slight vagaries in the performance, but it's not that important. What is fascinating, however, is that if we take the Go code, which I can't show you as stated, and we translate it to C#, which is trivial, and we run that, we get a radically different performance characteristic. And that is because the algorithm implemented for the Go code is substantially different than was the case for the C# code. And this tells us very clearly that what is not happening is the AI model, the LLM, is not somehow internalizing an understanding of the stated requirement from the prompt and then producing output for the language you requested. What it's clearly doing is trying to understand the gist of your requirement, figure out if it has seen a previous example of a similar output in that language, and then copying and pasting that for you. And that's kind of disturbing. So, in closing, having shown you some code and discussed some of the outcomes and observations, This is my two pennies worth in closing, as somebody with over 30 years of software engineering, soft coding experience, and an understanding of the mathematics of various things behind this. The truth is that AI models can produce code that is functionally correct, notably if your prompt is correct. So if you do not understand what the prompt needs to say, then don't use AI code models, because you're just going to be relying on junk as a simple truth. And I think everybody understands that you need to have the correct prompt. However, one thing that does concern me is, assuming you have a good prompt, if the model doesn't produce its best output at the first submission of the prompt, how would you know if it's capable of producing better output? That means that you would have to invest in expensive human resources, experienced software engineers' time, to assess the generated output in order to figure out whether it should be possible for the AI model to produce better output. And surely that kind of starts to suggest that maybe this AI code business is not really as cost efficient as people would have you believe. Another thing that's a problem is that these LLMs often, and this is our simple examples here of our rub salt in the wound code, is not a comprehensive coverage of this. I've seen far worse, but I have done a lot of experiments in this area, and AI code is very often extremely verbose. There's a lot of superfluous code in the output very often, and I suspect that it's often because they largely cut and paste. So they identify a rough requirement. They say, oh, I've seen code that satisfies this requirement somewhere in my training. I'll take that code and paste it in. But they don't seem to eliminate any code within their training code that isn't actually required for your problem. And this is obviously increases the cost of maintenance, of maintaining your code over time. And finally, it seems to be quite clear to me that these LLMs do not reason about the actual requirement in some kind of internalized form, and then produce output for the stated language. They seem to almost use training copy and paste code, or training input code that they've seen, as a rough heuristic of something that could satisfy the requirement, and then provide that as the output. The models do not appear to be at all capable of actually assessing the accuracy or suitability of that training code in the first place. So if the code upon which they are trained is invalid, you're going to get invalid outputs. There is going to be hallucination involved, and this is clearly a problem that people have been subjected to.